Morning, Tristan.
Good morning. How are you?
Good. How you doing?
I'm well.
It might be just you and me at this point. We'll see how it goes. It's not the first time that's happened, actually. I've had one person turn up to a class before.
You and I, and maybe about one other person.
What's that, sorry?
Yeah, I think last class it was just you and I.
And one other, yeah, you're probably right. Oh, well. Well, that's the thing. If I record them, I've always got the hope that people are going to watch the recording. And somebody pointed out to me the other day, that sometimes people don't want to attend because they just want to watch part of it. So, it's okay just to watch the recording. They can skip over the parts they don't want to see. I don't know. I don't know. That's my hope anyway, is that people are just watching what they want. All right, let's see. I've still got 45 seconds before we get started. Victoria saves the day. All right, 10 o'clock, we'll get started here. So this is the last Zoom session I'll be doing because next week is Thanksgiving and I won't be holding a Zoom session on Friday. So that's where we're at, folks. This is the last one. If you have any questions, need help with the final or whatever, let me know. I'll talk about the final a little bit here. Let me see what's going on with that. Oh. Final exam. I've got here that it starts at 10 a.m. and ends at 11 a.m. Now, what that means is that that's when I want you to start it in between those times. I think there's let me see what the time limit is. I think it's 2 hours. I'm just checking on that now. Yeah, it's 2 hours. So, but I'd like it started in between those times. Okay. So let's go back to module 11 here. I think module 12 isn't too bad. So I wasn't planning on going through that, certainly not today. So I don't think anybody's really in that place for it. Now, my washing's going, but it's almost done. So just bear with me for a couple of minutes. It'll be done soon, and that background noise will end up disappearing. All right, so let's take a look at module 11. Now, there's a couple of questions you're going to be asked, and one of them has to do with the speed of molecules. Let's see if is that it here? Yeah. So one of the things about gases is that the heavier a particle is, the slower it moves. So one of the questions you could be asked on test 4 has to do with the speed of molecules, and all you need to do here is just look at the molecular weight of each of these. So this would be about 74. This would be about 40, I think, 4, 32, 28. And then the heaviest ones will be slowest and the lightest ones will be fastest. So that's one of the possible questions that you might see on the test. Now, these other things that we talk about are all just about the rules that are associated with gases and the fact that we're dealing with what we call ideal gases, not real gases necessarily. One of the other things that's going to be important is our definition of standard temperature and pressure. 1 atmosphere, 760 millimeters of mercury, or 273 kelvins. The other thing that we're going to be talking about will be millimeters of mercury and torr as a temperature unit. 1 torr is 1 millimeter of mercury. So you'll see that those two are going to be used interchangeably throughout this module. And the other thing that's going to be important is that 1 mole of any gas occupies 22.414 litres at STP. And this is something we've used before in the other modules as well. We'll be making a lot of use of this combined gas law, which is the combined relationships between pressure, volume, and temperature, and that's P1V1 over T1 equals P2V2 over T2. The other thing we'll be looking at will be the ideal gas law, which is PV equals Nrt. One of the other questions you could be asked has to do with figuring out the molecular weight of a gas. And what we're doing there is we're using the density of the gas, which we're given here. And gases are always measured in grams per litre. Now, that might be something you're not really used to seeing as far as density goes. We usually deal with grams per milliliter. And what I'm saying there is that in gases, since they're more spread out, the density is usually measured in grams per litre. So the molecular weight of any gas can actually be measured by taking the density of that gas, which is in grams per litre, and multiplying it by the molar volume of the gas, which is 22.414 litres per 1 mole. And when we multiply those two things together, we come up with the molecular weight of the gas. So as long as we know the density, then we can always figure out the molecular weight. So one of the other questions you could be asked on the test has to do with figuring out which molecule might correspond to this specific density. And the idea would be here to take the 3.16, for example, and multiply it by 22.414, and that comes out to be 70.8. Now 70.8 would be probably Cl2. So you take whichever one has the molecular weight that is closest to what you calculate. Does anybody have any questions about example 2? Okay. The next concept we're going to talk about is partial pressures. Let me get rid of that. And what we know about gases, so let's say this would be an example of a gas. And let's say we've got a gas here that I'm going to denote by these circles here. And then we've got water down here. So when a gas is collected above water, we can measure its pressure, and the total pressure, which I'm going to call P total, is going to be the P of the gas plus the pressure of the water. So what's going to happen is you'll have water in the bottom of the flask here, but floating around above the water, you'll have these water molecules as well, and they're in the gas phase. So the total pressure, what we're measuring here using the pressure gauge, is going to be the pressure of the gas plus the pressure of water here as well. So if we know what the total pressure is, and we know what the pressure of water is, then we can calculate the pressure of the dry gas, that is the gas without the water. And the thing with the pressure of water is that it's all related to temperature through this table here, and it doesn't matter how much water we have. The vapor pressure of water will always be related to the temperature. So as long as you've got this table, you'll be able to always calculate the vapor pressure of the water. So in this instance, the question has to do with figuring out the partial pressure of the gas. So that's the gas without the water. So the total pressure was 790 millimeters of mercury. That's what's measured on this gauge here. The water pressure, or the pressure from the water, is going to be measured at 27 degrees Celsius. So we look at the vapor pressure chart here, we go for 27 and we see it's 26.7 millimeters of mercury. So that would be the pressure due to the water here. So when we have the pressure of the gas, it's going to be 790 millimeters of mercury minus 26.7 millimeters of mercury, which comes out to be 763 millimeters of mercury. So we'll have to do that occasionally when we're answering these questions, because we need to be able to figure out the pressure of just the gas without the water. Okay, so the first thing we're going to do here, now that we've got that background out the way, is we're going to start using this P1 V1 over T1 equals P2 V2 over T2. Now, in these kinds of situations, we're always dealing with two separate sets of conditions. So a good start is always to figure out what P1 V1 T1, P2 V2 and T2 are, also what we're looking for here. So we're looking for the volume of a gas, so that's what I'm going to put the question mark here. Now, whether we put it in P1 V1 T1 or P2 V2 T2 doesn't matter, as long as we're consistent about what we're doing. But when we're doing these kinds of problems, we have to be very cognizant of what information goes together. See, what we're looking for here is the calculation to calculate the volume of a gas at this specific pressure and this specific, well, and it'll be this specific temperature once we get down to it. But the key word here is this little word here, this at. So calculate the volume of a gas at 780.0 torr. So I know that we're looking at 780.0 torr as being the pressure. Now it also says if 500.0 mils is collected at 30 degrees Celsius, and the temperature here has to be measured in Kelvin. So that's where the 303 comes into play. And we're also told that it's at 730.0 torr. So all of that information is together. And it does say also the temperature remaining constant, which means just that the temperature is going to be the same. So the key thing here is to be able to group the information. Figuring out what the pressures, volumes and temperatures are is not really that difficult, because the pressures will always be measured in torr or millimeters of mercury or atmospheres. The volumes will always be milliliters or liters, and the temperatures will always be degrees Celsius or Kelvin. The problem lies in figuring out what information goes with which. Once we've obtained what's what, then we can solve for the information we're missing, which is the V2 here. And one of the tricks we can use is just an algebraic trick here that allows us to move something that's on the bottom to the top on the other side and something that's on the top to the bottom on the other side. And really all we're doing there is multiplying both sides by T2 and dividing both sides by P2. Then it's just plug and chug from that point. So I'm just substituting what I see here in T2, that's 303, over 303K times pressure to 780.0 torr. Now you'll notice that after I go through all of this, that the torrs will cancel, the kelvins will also cancel, and all we'll be left with is milliliters, which is what we were looking for in the first place, which comes out to be 468 mils. Does anybody have any questions about what we're doing here?
Negative.
As I said, the hardest part is this part here, identifying P1, V1, T1, P2, V2, and T2. And that's going to be my main focus in the rest of these problems, not so much this rearrangement part, which I don't feel is too difficult, but this is going to be a constant thing that you'll see as well as we go through these.
I was gonna say I'm glad you said that because I have to read the question like 3 or 4 times.
Right.
Right. I mean, I'm getting better at it, but yeah, I'm glad I acknowledge that that's kind of hard sometimes.
Oh, no, it is. I mean, take a look at this as well. Your volume of a gas at, so you know that the volume of the gas you're looking for is at that pressure. So you know that those bits of information go together. But you can also see this 500 mils is collected at 30 degrees Celsius. And so you see that all of that goes together as well on the other side.
I see what you're saying.
So it's a little bit of, it's a little bit about being able to interpret the word problem as well. And I know that that's not something a lot of people like, is having to do that. I get that. Let's see. Let's take a look at this example 5 here. Now, one of the other things I'll point out is that none of what we've dealt with so far has anything, collected over water. But let's look at this one here. We'll see if we can identify which bits go with which bits. So we've got P1, V1, and T1, P2, V2, and T2.
Actually, I did have a question about that.
Yes.
So one of the problems, it was collected over water, and then I did the calculation, right? But then it says like the second pressure, the total of the second pressure, and I also subtracted the pressure from the water on the second part. But I got it wrong. I mean, I went to the video and saw that it was supposed to stay the same, but I don't understand why if it's the total pressure.
All right. Well, it's only it's just that the second set of conditions that you're looking for, that's the only part that's collected over water. The rest of it wasn't. And
okay,
you've got to make that assumption there was no water initially.
Okay, I got you.
But I do get where you're coming from with that. But let's take a look at this one here. Gas, 100.0 mils. So I'm going to make that V1 here. Has a pressure of 750.0, so we know that's under the same conditions, so 750.0 millimeters of mercury. And we're given a temperature here, which I'm going to immediately convert into Kelvin to 98K. On the other side, what are we looking for? We're looking for the temperature. So I'll put a question mark there. Then it says the pressure is changed to 780.0 millimeters of mercury. And the new volume is 200.0 mils. Now, when you're looking for a temperature or trying to sort out a temperature, I think a good technique here is to put both temperatures on top by flipping both sides. And that way we can isolate the temperature a little bit more easily. It's not to say you couldn't do it another way, but That's what I'm finding here. Okay, does anybody have any questions? So after that, it's just plug and chug. It's plugging all these values in and coming out with that temperature at the end. Does anybody have any questions about how I assigned P1, V1, T1 and P2, V2 and T2? Because that's really the key here. Anybody have any questions about that? Okay. Now this one's interesting. So Zave, this is one of those that you were talking about.
Okay.
Where we're dealing with over water here. So what we're looking at is calculating the volume of a gas at STP. Now this is interesting, the way we set this up. So we'll do our P1, V1, T1, P2, V2, and T2. So look what it says here, calculate the volume of a gas at STP. I always see at as being the most important word here in the word problem. It's going to be the at. So the volume, that's what we're looking for, and we're looking for it at STP, which is going to be 760 millimeters of mercury or 760 torr. I'm using torr just because we've got torr over here as well. And 273 K. See, the thing is that STP, standard temperature and pressure, is always 1 atmosphere, which is 760 torr, or millimeters of mercury, which is really the same thing, at 273 K. Does anybody have any questions?
How come it's not 760 or it's not 730 torr?
Oh, we haven't gotten to the rest of it yet.
Oh, okay.
I'm just talking about the first part. So the second pressure is 730 torr, right? And the volume is 500.0 mils. Now, we're not done with the pressure yet. I'll get to that in a second. And this would be 303 K. Now, it does say collected over water. So we are going to have to subtract out the pressure due to the water here, which is 31.8 millimeters of mercury. So what I want you to understand here, or 31.8 torr, is that this pressure would remain the same if it didn't say over water. Now, Zave, to answer your earlier question, what Zave was asking earlier is he was saying that he also subtracted the 31.8 from the 760, or he did a similar problem where he had to do that. But the thing is, what we're looking for here, you've got to assume that we're calculating the volume of the gas and it doesn't say over water. Now, if I said calculate the volume of the gas over water, that'd be a different kettle of fish, Zave.
Okay, yeah, I can understand that.
But it was a good question. I do appreciate it. Does anybody have any questions about this one? So once we've done that, we do the isolation thing just as we did previously in that example 4 that I showed you earlier. And then we can calculate the volume. But the main thing is understanding what this at means. We're looking for the volume of the gas at STP. That's why I put the question mark there. And then I had the STP pressure and the STP temperature down here as well. And that's due to this knowledge here that STP is those specific conditions, standard temperature and pressure. All right, does anybody have any questions? About number 6. Okay. All right, so let's look at PV equals nRT. Now these are different kinds of problems because they will now bring into play N, which is going to be number of moles. And this can also then equate to grams as well. So if we've got grams, then we can find number of moles by using the molecular weight. So these problems are distinct from the ones we were just looking at in that we only have one set of conditions, and we're also going to be dealing with moles or grams as well. So for this particular one, this one's actually fairly trivial, but I'm going to go ahead and do it anyway. So in a PV equals nRT problem, we've got the pressure now at STP, that's going to be 1 atmosphere. The volume is 250 dot mils. N is what we're looking for, number of moles. Now R is always given to you. It's a constant value. Oops. With constant units. So it's 0.08206 liters atmospheres per mole per Kelvin. You don't have to memorize that, you'll always be given that. The temperature is 273 K because we're dealing with, again, STP. So to solve for N, we know that PV equals nRT. So N is equal to PV divided by RT. And then we just plug in our values. So we'll have 1 atmosphere times the volume. Oh, now here's this ends up being a wrinkle now. So you've got milliliters here, we've got liters here. So I better check myself here and say, okay, well, I better convert that into liters so that those units match, otherwise they're not going to cancel. The R value, 0.08206 liters atmospheres per mole per Kelvin. And that's times the temperature, which is 273 K. So once you do all that math, it comes out to be, in this case, 0.0112 moles. So the key here is to make sure that all of these units that we come up with match the units that we're given in our R value. And as I said, you're always going to be given, actually moles is what we're looking for in that case. Does anybody have any questions about using PV equals nRT, something like that? Let's look at something a little bit more. Okay, we'll do this example here. Again, it's a PV equals nRT problem because it involves moles, and you can see that. Now, the thing we're looking for here is pressure. So I'll put a question mark there. The volume is 5.75 liters. The N is 0.414 moles. The R is always going to be what I said it was, 0.08206 liters atmospheres per mole per Kelvin. And the temperature here is 312 K. So you can see that the units match. We're looking for atmospheres. So everything matches. So now I know that P, V equals nRT, and P would be nRT divided by V, and that should give me my answer. And you can see it does 1.84 atmospheres is what it comes up with at the end. Anybody have any questions? Let's take a look at this one here. This one involves a little bit of a conversion. So I'll show you this one. So again, you know that we're dealing with PV equals nRT because we've got moles in there. So we do PV and RT. The pressure is 766 torr. The volume is 14.2 litres. The N is 0.955 mole. The R is 0.08206 litres atmospheres per mole per K. And the temperature here is given as, well, temperature is what we're looking for, right? And that's going to be in, what's it after? Well, it doesn't say what temperature. It's probably going to be measured in Kelvin though at the end. Now you'll notice that we have litres and litres, that matches, moles and moles, that matches. What we don't have though is this match between torr and atmosphere. So I'm going to have to do a conversion here. And the conversion is 1 atmosphere over 760 torr, which comes out to be 1.01 atmospheres. So PV equals nRT. If I want temperature, it's going to be PV divided by nR. And if I do that and substitute all those values in, that'll come out the right answer, which will be 183 K. Does anybody have any questions? Okay, now this can be extended a little bit. And what we can do is we can actually find the molecular weight given similar kinds of data. Now the key with molecular weight is that it's always the mass of something divided by the number of moles you have for it. So it comes out to be grams per mole. Now you'll notice in the problem we've got grams, 1.324 grams. So we don't have to worry about that. That's something we already have. What we don't have is the number of moles. And to get the number of moles, then we can use our PV equals nRT and we can solve for moles. So this is a really good example of this because I have to do a lot of converting in order to make these units match. So we've got litres, atmospheres per mole per Kelvin. Now the pressure here is 780 torr. That needs to be in atmospheres, so I'll do my conversion here. And that comes out to be 1.03 atmospheres. The volume is 150.0 mils. That needs to be in litres. And the temperature is 100 degrees Celsius, and that needs to be converted into Kelvin. So again, PV equals nRT. We need N. And once we calculate that by substituting all those values in, we get 0.00505 moles. To get the molecular weight, we take the mass we were given in the problem, which is 1.324 grams. And we divide it by the number of moles that we see here. And that comes out to be 262 grams per mole. So that's how we would calculate the molecular weight of that gas. So this is actually something that chemists will do in order to figure out the molecular weight of a gas. They'll measure its mass, they'll measure its pressure, they'll measure its volume, and figure out the temperature and figure out the number of moles, and then they can calculate the molecular weight of it, which can help identify it. Does anybody have any questions about this kind of problem? Okay. I think this is the last one, this last kind of problem here. This last kind of problem allows us to extend what we know about stoichiometry into gases here as well. So you'll notice that we've got calcium carbonate, we're given a mass of that, but what we're looking for is a volume of carbon dioxide gas. So we've got 275 grams of calcium carbonate. We want to figure out the volume of CO2 gas that we're going to get from that. So the aim here would be to figure out how many moles of CO2 we're actually dealing with here. So let me extend this out a bit. So the method of solving this problem is we're looking for the volume of CO2, but in order to do that, we need the number of moles of CO2. We are given the pressure and the temperature here. So you can see we've got T and P. What we don't have is N. So the way we get the N is via this stoichiometry here, where we take the 275 grams of CaCO3 and convert it into moles of CO2. And what we're doing here is we're using this modified flow chart here. But all we're interested in is moles of B, or moles of CO2 here. So the way we do that is we use 275 grams of CaCO3. We need to figure out how many moles we have of that. So it's 1 mole of CaCO3 over 100.09 grams. And then we need to take into account the mole ratio as well. And it's 1 mole of CaCO3 gives 1 mole of CO2 gas. Oops. Moles of CO2 goes on top. 1 mole of CO3 goes on the bottom. There we go. And that comes out to be 2.75 moles of CO2. Now, once we've got the moles of CO2, then we can use PV equals nRT. Because the pressures and temperatures, or pressure and temperature that we're quoted, is going to be for the CO2, so it's 1.25 atmospheres. The volume is what we're looking for. The N is 2.75 moles. The R is 0.08206 liters atmospheres per mole per Kelvin. And the temperature is what we're given in the problem, 567 K. So you'll notice that everything matches up, and we can do our PV equals nRT. And V equals nRT over P, which allows us to get the volume of CO2 here, which would be 102 liters. All right, does anybody have any questions about this example here, example 14? With these kinds of problems, you're always given a chemical reaction that's already balanced. So you will already sort of have a cue as to what you need to do there. Once you see that reaction, you'll think, oh gosh, I'm going to probably need a volume of something, moles of something from that. Moles of a gas is what you'll need. All right, any questions? All right, let's take a look at the kinds of problems you're going to see in the assignment. Remembering, of course, that the assignment problems all have videos as well.
Yeah, I use those.
That's good. I think more people should. But, you know, as long as you go through the videos, it's hard to see how one could fail the assignment, especially if you can do it multiple times. Let's see. Yeah, I want to go through something like, well, question 4. I think I already, well, let's look at question 5. We'll do that one. So you'll notice the way it's set up here is P1, B1, T1, P2, V2, and T2. And I've arbitrarily assigned V2 as being the answer because we're looking for a volume. So let's look at how we might go about doing this. Now the 459 mils, that's the answer. So that is going to be automatically number 5 because that's what we're looking for. It says determine the volume of a gas at STP. Now that volume is at STP. So STP is going to be P2 and T2, which means that T2 is going to be 273K. So that's going to be number 6. And P2 will be 1 atmosphere, or in this case, 760 millimeters of mercury. So that'll be number 4. And it's collected over water at 50 degrees Celsius, which is going to be 323K. So that's going to be number 3. The volume is 600.0 mils. So that's going to be number 2. And it does say it's collected over water at 780.0 torr. So it's not 780.0 torr, it's going to be 687.5 torr. So that's going to be number 1. Now, the way we get that is to take the 780 that's given here and subtract out the vapor pressure due to water at 50.0 degrees Celsius, and that will give us 687.5. This one here is blank, it gets the unused answer. So that was the wrong answer to use for the pressure. So that's how you would do that. Does anybody have any questions about setting that up? My recommendation, I mean, I did that, you know, obviously without writing it down. You could, as you're getting used to these, it's probably a good idea to write it down on a pen and paper and do it that way rather than just do it in your head like I just did it just now. But I am showing you could do it that way if you wanted to. So a lot of them are very similar to that. Then the PV equals Nrt problems and the grams per mole problems are here as well. Let's see. Yeah, so this is a PV equals Nrt problem. And you can see it's a matching problem as well. You got pressure, volume, moles, R, etc. And then the unused answers. Make sure you put the unused answers in as well. So I don't know, I don't think the assignment is very hard. I just see it probably a little bit annoying, really, having to match everything up. But it does certainly test what you're doing, and you certainly will understand what you're doing after going through and doing the assignment. Does anybody have any questions about the assignment?
No, that's pretty straightforward.
You'll have to practice quiz as well. And the setup is very similar, except now you're actually typing stuff in. So if you're uncertain about the formatting, you know, spaces and whatever else, my recommendation would be not even to start the practice assignment first, but to go down to the very bottom and just submit it and take a look at the answers. Just like I'm doing here. And that will tell you what the formatting is. Remember, the parentheses aren't part of the answer, right? So whatever's in here, that's what's expected. You'll also notice, and I think this is an important point, 500 dot mils is what's expected here. If you put 500 mils without the dot, it's not going to mark you correct. And I'm not going to go in and correct it either, because 500 mils and 500 dot mils are two different things. You know, this is something we talked about as far as the significant figures go. So make sure that if you're given a value, that you use it exactly as it appears, and don't try and shortcut it. All right, does anybody have any questions? Okay, well, that's pretty much all I had wanted to go through today. And as I said, there won't be a Zoom meeting next Friday because it's Thanksgiving. And let's have a look at the schedule here. Just make sure everybody's on the same page with the schedule. We've got module 11, which is due on Sunday. Module 12 is due a week after that, November 29th. Practice test 4 extra credit closes on December 1st, and the test 4 is going to be due on December 2nd. The final will be due will be due Monday, December 7th, and you have to start between 10 a.m. and 11 a.m. That's not to say that you have an hour, you have 2 hours, but you have to start between those times. All right, does anybody have any questions? Okay, well, then that's it. Nobody has anything else. We'll end it here today. I do appreciate you coming. Thank you.
Thank you.
All right, see you later.
All right, thanks.
Now, you have to wait until December 5th, Tristan. Did you get me, Tristan?